size. Okay. So we update the value at time k and at the nth grid point by subtracting sigma times the difference of the value at this grid point minus the value of the left neighbor. And there was a question in the Slack by Abdel. I will please, if I don't remember, please remind me of that. He asked the very good question. We do a forward finite difference in time, and we do a backward finite difference in space. Yeah, you see. Here we do a forward finite difference, and here we so we take compare k plus 1 and k, and here we compare n and n minus 1. Why do we do that? We could do it in another way as well, but it has to do something with the information flow. Yeah. So this is a very simple equation how we can update it, and this is the Python implementation. So and I want to discuss a few things about the Python implementation here in the tutorial as well. Again, this is our initial condition, 0, u0 shall store our initial condition. I want to save this as u0, and I make a copy of that into u. You will hold the solution at time. We don't want to save it at every time step. We only want to have the current solution, the solution now at the moment. And what okay, so I want to have a copy of u with u0. There's one thing. Maybe I can ask you. So sorry, let me go to the to Slack. So and the question. So Tudukila told me that it's possible that you raise your hands and ask direct questions. Or you can also write into either the Slack chat or in the webinar chat. You can ask your questions or raise your hand, and maybe Tugila is able to unmute you. And you can ask your question via your microphone or your answer. So now I would like you to answer either in the chat or raise your hands. What do you think? Why don't I write u equals u0? Any idea? So my intention is I want to save, I want to keep the value of the initial condition. Yeah, this will be a Gaussian function, right? u0 is the initial condition, or the function corresponding the function. Yes. Yeah. Okay. Yes. And Mark and Tracy gave the correct answer. Yeah. If I did this, u equals u0, this would mean that u and these are Python objects, yeah, right? That means in Python that u and u0 are exactly the same, pointing this to the same object, which means whenever I update u, I would also change u0. Yeah. So what I need is really a copy. I don't want to have this just a pointer to the same object. I don't want them to point to the same object, but I want to have two objects where that both can contain at the first step the same information. Yeah, that's why I choose this. I'm a lazy guy. I occasionally do the following. I write this as 1.0 times u0. This does the same thing. Because this is now a NumPy operation, and all these math operations create new objects. Yeah, so that would be the same. so I need a copy. Yeah, thank you very much. Yeah, update also came up with the correct answer. Okay. Now we I don't remember. Let me repeat what is the code. We first set the current time to so the small one, small t is the current time, and capital T is the time where we would like to stop. No, so we set the current time to 0, and now while the current time is less than 1, we update the time by adding time step dt. Yeah. I guess you know this shorthand. This is a shorthand for t equals t plus dt. Now it's nicer to write it this way. Yeah, and what we do here is we do on the array of vectors of all points apart from the first data point. Yeah, we start at the second. Second has index. Yeah, first the leftmost data function value is at x equals 0, and the last one corresponds to x equals n times delta x. Yeah, so for all, starting from this second data point, so these are all the inner data points, plus the last data point, update them all by subtracting, yeah, so here's a minus equal, subtracting sigma times the difference of the current, of the value at the current position, minus the value at the left neighbor. You know, what is the array of left neighbors? It's just shifted, the array shifted by 1. Yeah? So it starts at the left neighbors start at 0, and they go -1 corresponds to the last data point. But remember, it's Python. And in Python, we go only, the last data point is excluded. Yeah, so this means 0 to -1 means go from the first entry to up to the next to the last entry. Yeah, do this update there. And on the boundary, I said we choose periodic boundary conditions. On the boundary, whatever is leaving on the left gets in on the right, yeah, and this means we have to copy. Do what is the left neighbor of the very first data point? It's the last one, yeah, because it's periodic. So we have to update this last one with these values. Okay, and I don't know whether you have seen the solution. Let's do this for a few time steps. Solution looks like this. This is the blue thing is the initial condition. Yeah, that's why I saved it. And U is and this is U. Yeah, so I'm plotting both the initial condition and I'm plotting U. Now this is the updated value at time capital T equal to 1. What should be the solution? We have computed the analytical solution. What do we expect? We have solved the problem analytically using the method of characteristics. And the method of characteristics says it's here we have it. It's the initial condition, but evaluated at position x minus at. Yeah, so we have it shifted by, remember, a was set to 1 and capital T is set to 1. So this is at f of x minus 1. This means that the solution actually should be the original function, but moved one field by 1 to the left, by x to 1 equals 1 to the left. Yeah? You see, we have the maximum. We have it here at 5, and here actually it's at 6. No? When we zoom in, the maximum moves from 5 to 6. So this looks nice. And we should be moderately happy about it, at least moderately happy. So that was the end of the talk, of the lecture. And,
Prof, there's a question on Slack.
Yeah. Okay. Could you please let me know why you can't use U0 directly? I could do the same with U0, but then I would overwrite it. Okay. I can mimic this by if I say U equals U0, this would override, then U and U0 are the same object. And that means when I overwrite something in U, I will overwrite also U0. Yeah? And then it would look like this. You see, then both are the same. In order to save the solution, I have to make U0 a copy. I hope this answers the question. No, U0 is not the exact solution. U0 is the initial condition. Yeah. And we know from the method of characteristics the solution of U of xt. So this is what I called U0. Sorry, no, the initial condition was F. Yeah. Here, initial condition is F. Let me recode it. Sorry, this was maybe a little bit confusing. I will rename it not U0 because I'm usually using U0, so I didn't want to mess this up. And then I plot F rather than U0. Do it again. F. So F is the initial condition. So the determined by the initial condition. So this is the solution at time 0, and this. So the blue is the solution at time 0, and orange is the solution at time t. Let's solution at t equals 0, and this is the numerical solution of the finite difference solution at time t. Okay. Sorry, missing. Yeah. So U is this solution for a fixed time t. Yeah. This is capital T. Yeah. I do this. I iterate this again and again until I have reached the solution. So what would happen? What do you think? What would happen if I say t equals 5? What would happen? What would be the difference? Maybe you can write down the solution in the chat. Now I move to t equals 5. Yeah, the solution will change, certainly. Any idea how it will change? Somebody's writing. I will wait for a second. Okay. Forward shift of the orange curve. Exactly. Yeah. The orange curve is now shifted by 1, and then we expect it, if our analytical solution is true, we expect it to be shifted to A is 1, T is 5. So the solution will now be X minus 5. It's shifted by 5, or should be shifted by 5. Let's see what if this happens, if this is true. Yeah. So we simulate it and we plot it, and you see it's true. It works. Now, if I go to t equals 15, it should work again. Now let's go to t equals, you see the peak has now moved from 5 to 5 plus 15, to 20. And the solution otherwise is, apart from possible numerical errors, it's completely the same. So it looks very, very nice. Let's go ahead by 25 steps. And sorry, by 20 steps, then it should be should have moved to a position 25. Keep in mind, this is a numerical solution. Yeah, this is different from the method of characteristics. We have done this numerically here now. Now, my next question to you is, okay, we are coming closer and closer to the right boundary. What will happen if I say, so here we are, if I go to time equals 25, what will happen then? You see, we expect that the peak should move to 30, but what will happen to the curve? We leave our interval now. What will happen? I prepared the simulation. So now we will make 25 time steps. I run the simulation and I don't show the figure yet. Maybe you can, does anybody come up with a solution? Yeah, I said we have a periodic boundary condition. Yeah, so what leaves on the so the left neighbor of the leftmost data point of 0 is the rightmost data point. So every piece of matter that leaves through the right boundary re-enters through the left boundary. So if I didn't make a mistake, this means that the solution now should move to the right a little bit again, but that part that is cut off should begin to show up on the left-hand side again. Yeah, so let's see whether this works, and you see it works. Yeah, so the peak is shifted to 30 to the right boundary, but you see the information is entering through the left boundary again. Yeah, which means that if we proceed by 30, the solutions should lie above each other again. Yeah, and you see, of course, we have a small numerical error, but otherwise it works. They should be exactly the same, and they are pretty close to the same. Yeah, and at 35 we should be again at a position it should move forward again. And it would repeat this for until eternity. So we have our first numerical solution, and it looks so far quite nice. And yeah, reason to celebrate. Yeah, so there's interjection by Mlugisi. I think the maxima will change. We'll have different endpoints boundaries. Yeah. Oh, okay. I guess this was an answer to my previous question. So, okay. I thought that's a new comment. Okay. Fine. Are there questions so far? As I told you, I encourage you also to raise your hands and ask questions. We will see. Tutu Kile said that it's possible or should be possible to get questions there. Otherwise, you can use the chat to ask questions. Okay, if this is not the case, I come back to, maybe this is a good opportunity to come back to the question by Abdel.
Sorry, Prof, there is a hand from Mohammed. Mohammed,
okay.
You can go ahead.
Yes.
Mohammed, I gave you permission to unmute yourself. You can go ahead and ask your question.
Seems that it doesn't work.
You are unmuted, but we can't hear you. You can go ahead, Mohammed.
Okay, I think it's not.
Okay.
Okay, yeah. Okay, sorry for that. It seems that it's not possible to ask questions via microphone. Sorry. Yeah. Okay, there's another good question. Yeah. Okay. Hopefully we'll get the question by via chat. Okay. During this time, I try to answer the questions by Abdel and Lungisi. They are very good questions because I wanted to emphasize these points. Let me start with, because Abdel's questions is a little bit more complicated to answer. Let me start with the question of Lungisi. And the question is, what if we decrease delta x to a limit of 0? Yeah, and this is very much related to the following thing. I purposefully introduced this parameter sigma, and I will print sigma. Yes. Let me print sigma. So I chose sigma equal to 1. And now I modify the question of Nungisi a little bit. I don't modify delta x. We can modify delta x, by the way, by increasing the number of grid points. Let's take 500 grid points instead of 200, and we see the solution looks a bit smoother then because we have more grid points, yeah? But it's basically the same result. Yeah. Okay, now it looks nicer because we have more grid points. It doesn't look as bumpy as before. But now, tendency, if we make delta x smaller and smaller, the smaller we make delta x, the better the solution will be. But of course, we don't, for this case, we don't see much of a difference. Let me go back to 200 in order to demonstrate you a few things later. Yeah, what would happen if I mean, dx, this is the time, we measured in seconds. Dt is a time, we measured in seconds. Dx is a space variable, we measured in meters or centimeters. So these are completely unrelated things. Yeah? What if I made dt smaller? Let's make dt smaller by a factor of 10 and see what happens. Let's take have dx fixed. So I modify the question by Lungisi, but by taking dt smaller. Yeah? So dt is smaller by a factor of 10. And I will print sigma again. Okay, so sigma is now 0.1. And now let's plot the solutions. And now we should be a little bit unhappy. Yeah, because one aspect is the same. Our solution, our peak has shifted by 5. Perfect. But the shape has been changed. And this is a phenomenon called numerical diffusion. So actually, it's good to have sigma close to 1. So 8 times dt, as same would happen. So if we set a equal to 10, for instance, let me go. Let me set no. Let's stick to that. So the phenomenon will also be visible here. Yeah, you see, for one time step, the peak has moved moved by 1, but the solution has become wider. Let's do 2 time steps. Maybe it's a little bit better to see then. Yeah. The solution has definitely widened. I think this is very clear to see with the naked eye. And actually, this is a numerical artifact. This is an undesired thing called numerical dispersion or a numerical diffusion. It's a it's a discretization error. It's an error that we make because we consider the function only at finite sizes and that we approximate the derivative with the finite differences. And the magic is, if I make this velocity larger again, such that the sigma equals 1, we see that it's fixed. So the thing is, when sigma equals 1, we don't get numerical diffusion. Actually, one can understand it with the method of characteristics, because then the information, if you look into the equations again, the information is carried along the characteristic, along the exact characteristic. So the characteristics connect the x, the grid, the characteristics connect the data points. So the information for sigma equals to 1, the information is flowing exactly along a characteristic, and therefore we get the this numerical scheme gives us the exact solution. And no, but if we make sigma smaller, we are no longer exactly on the characteristic, but the characteristics are connecting parts of the interval with other parts of the next interval. Yeah. So we don't, the grid points are not on the characteristics, so we get some incorrect information. So for sigma equals 0.2, this is so if sigma is less than 1, we get this effect that we have numerical diffusion. This shows up in every scheme. One can improve it using higher order finite differences. There is a thing, I cannot go into this because this it would take time. It doesn't take much more complicated mathematics, but it would take time to discuss and understand it. So the famous scheme is the Lex-Wendroff scheme. And then there's also a predictor corrector method that predicts a step and then makes a correction to the thing. And for linear equations, this is exactly the same as the Lex-Wendroff scheme. For nonlinear equations, there are some subtle differences. So I won't go into details with that. Huh? So if sigma is less than 1, we get this effect of numerical diffusion. We can also ask, what is or let me first ask whether there are see whether there are questions in the chat concerning numerical diffusion. It's worse the smaller we make the time step. Yeah. So if we make it's getting worse. Yeah? If we make sigma smaller again, let's say again by a factor of 10. You may or may not see it. It's getting worse again. Let's look at the peaks. Yeah? So it's smoothed out. Actually, it is a diffusion. You can represent this numerical diffusion. This is a diffusion. It's a second order effect. Yeah? This smooths out the solution. So something, what is going, some information is flowing from the peaks to the sides of the, and you see, this is for sigma equals to 0.1. We have about 20% loss in the peak. And let's get back to 0.1. Okay, this is almost exactly the same. This is a bit surprised, maybe not. Maybe we go the other way around. Let's take a moderate value, 0.9. And you see that then the effect is much less pronounced. It's getting a bit lower and a bit wider, but not as much. Yeah, and so it's getting worse when sigma is becoming smaller. Yeah? So here for sigma, we are at maybe 95, 97% of the peak. And for sigma equals 0.5, you see it's closer to this 80%. Yeah? And at 0.1, we get this 80%, and this it seems to saturate. Okay, so that's one of the problems that can occur. We can also ask what will happen if we make sigma larger than 1? Yeah? Why not take dt equal to twice the time steps? Then sigma will be, because a is 0, a dt over dx will be 2. Sigma will be 2. Yeah, you see. And what will the solution then look like? Yeah, you see that there we have a kind of counter effect. the solution seems to have become a bit narrower, and it's increasing, and it's becoming negative in some parts. Yeah, and actually this is very dangerous. Let's make the solution evolve for a longer time, for 20 time steps. You see there are some horrible oscillations. This is a so-called instability. The algorithm becomes unstable if we make this sigma too large. This is also another frequently occurring phenomenon in in the solution of numerical solution of differential equations. It's problematic when the time step becomes too large. Yeah, then you get instabilities. And you see, it's not harmless. It's wildly fluctuating. The solution is wildly fluctuating, and remember, the solution was between 0 and 1, and now the values are suddenly at 10 to the power of 19, more than 2 times 10 to the power of 19, or minus 2 to the power of 10 to the power of 19. Yeah. So these are huge, and yeah. So if it will get worse and worse when we might make more time steps. Yeah. So here, after 40, at t equals 40, would have a 10 to the power of 51. So this is a bad idea. You cannot make dt larger than sigma larger than 1, and sigma equals 1 hits the sweet spot. So one could ask, oh, this is the solution of everything. I should just take care that sigma equals 1. There's one problem with that. Often we had a simple case where this velocity is a constant, but in many applications, and we will see one later in the Burgers equation, a is not a constant, or this velocity that is standing before u. Yeah, in this equation, you can imagine that that we have this equation here. This equation, and a is not a constant, but a function of x or a function of t. And if it's a function of x, you cannot guarantee that, or you cannot achieve that sigma is equal to 1 for all data points, yeah? Because you have a regular grid and the velocity is different at different points of the regular grid. So you can only achieve that sigma is less than or equal. You will want to avoid that it's bigger, that it's becoming bigger than 1. But you have to guarantee that it is less than or equal to 1. Yeah, and if a is not constant, and a may also depend on u itself, we will see the Burgers equation as an example. Then you will always have numerical diffusion as a problem, and may need to resort to other schemes like Lex-Wendorf or McCormick. But what we should also emphasize, it helps when it helps to decrease the grid size. Yeah. So let's get back to the numerical diffusion. Yeah. So let's go to t equals 5. Just let me make sure. Yeah. So we get the exact solution if we can guarantee that sigma equals 1. So a times delta t over delta x equals 1. That's in a way numerically the perfect situation. Otherwise, if it's bigger than 1, we get instability. If it's smaller than 1, we get numerical diffusion. Numerical diffusion is by far not as bad as instability, because instability gives you, in most cases, unreasonable solutions, and numerical diffusion is something you can cope with. And yeah, let's increase the no, let's first look at the solution with 0.1 again. So you see, We have considerable numerical diffusion. And now increase the grid size by a factor of 2, by a certain factor. And you see, now then it's much better. If we decrease the grid size, we didn't change sigma, it's still 0.1, but for a smaller grid size, that is one possibility, one brute force possibility to counteract numerical diffusion. So if we make the grid size bigger and bigger, then numerical diffusion becomes less and less problematic. Yeah? You see, here it's almost fine again. So one possibility is to decrease the grid size, which of course requires more computation. Of course, the nice thing is you get a finer resolution. The solution looks nicer, very smooth, but computation time gets longer. Okay, while let's see what happens with numerical with the instability. Yeah, let's go to the unstable situation again. Here's, you see, you have this instability, the oscillations. Let's increase the number of grid points. And you see, making delta x smaller doesn't help you much about against the instability problem. Actually, it's getting worse here. Yeah, so the solution with 200 grid points is not very good, but it's definitely not as bad as the solution with very large number of grid points. Now, let's make it 5,000, and you see 10 to the power of 186. This is crazy. Yeah. So now, while if we go to the stable regime, everything is fine again. Okay, so I'll give you a little bit of time to write questions in the chat. Or if you want to make me experiment with some of the parameters, please go ahead. Okay, then now it's time to get back to Abdel's question. Thank you very much for this question. Yeah, so Abdel asked the question: why do we take the backward difference for the position and the forward difference for the time t? And the answer is we take a backward let's assume that we take a forward difference in position. Yeah, what would be the forward difference in position? Yeah. That means that we go here from un plus 1 minus ukn plus 1 minus ukn. That would be the forward difference in the position. Yeah. Okay. Let me show it on the whiteboard. So we had our initial condition, and we know by our let me find I print this solution in red. Yeah. So we know what happens with the solution. So this is f of x. Let me write this in blue letters. This is our initial condition f of x. or our initial distribution f of x. And we know what happens. We know from the method of characteristics what happens. The solution will move to the right. So at a later time, it will be just shifted. Okay, here I have added a little bit of kind of numerical diffusion, so maybe it will. I hope you see what I mean. Yeah. So the solution will be just shifted to the right. That means we have an information flow that goes from the left to the right. Yeah, for if A equals A is bigger than 0. A is the transport velocity. Yeah. A is a velocity. The information, so the mass that enters a certain interval comes from the left. Or if it decreases, it goes to the right. It comes from the left and goes to the right. So now consider what would happen if we have take the backward the difference in this backward direction. Then we would update the information here of we need the update from the left data point, but we get it from the right data point. And actually, this is an unfavored solution. Yeah, so one takes this is a so-called forward upwind scheme. Yeah, for A larger than 1, use forward differences. Sorry, use backward differences. Because the backward difference takes updates. So UKN equals UKN plus sigma times the difference UK minus UKN minus 1. Yeah. So so this is sigma. Yeah. We get the information from the left neighbor because the information is flowing from the left to the right. Yeah. Sorry, this is a minus. Yeah, nevertheless, information is flowing from the left to the right. Yeah, whether you sum it or subtract it. Yeah, it would be different if and so if we take the forward differences, there's no chance that we get the correct information. However, if we need the information from the data point from the left, yeah? So this will update. Will be the correct update. We need information about what is coming from the left side. The thing is the other way around. When A is less than 0. No? Then we would need the information to come from the left, so for A, if A is negative, then we use the forward finite differences. I hope this answers the question. And let's see what happens if we are doing it wrong. So I don't want to change the code too much. Yeah. So we could use oh, sorry, I'm in the wrong inter. So we could do the updates to the left. sorry, we could modify this to use backward differences, but what would be an equivalent, we can make the velocity. We can make the velocity run into the wrong direction. Yeah, so we can make the flow run from left to the right. Sorry, from right to the left. A negative velocity would make the transport. Would make the update moving from, or would make the curve move from right to the left, not from left to the right. And see what, let's see what happens then with our numerical scheme. Yeah? Again, to make sure that everything's fine so far. Let's see, this gives us the correct solution. And now I do a seemingly harmless thing. I reverse the direction. And you see, this is really, really bad. We get instability again. Now, this is an unstable scheme. And the origin is that we are moving into the wrong direction. Yeah, we are getting information from the wrong neighbors. Because now we would have to get the information from the right neighbors, but not from the left neighbors. And actually, it's also bad. One might consider higher order derivatives, which we may or may not discuss later today. But let's not go into details too much here. No? So keep in mind that you have to take into account for this transport. If you see the parts alpha something times the space derivative, you usually can interpret this as velocity times so a kind of a velocity term that transports the information from the left to the right if A is positive, and right to the left if A is negative. I think that's a very useful interpretation for solving partial differential equations. And we will see in this afternoon an application to the nonlinear Burgers equation, where we find some interesting facts about nonlinearities. Okay, now so I corrected it. Now the information is coming from the correct direction. And everything is fine again. But you see, it's not easy without some deeper understanding. I think so. Abdel's question was completely valid. You know, why should we take backward differences? We could also use forward differences, you know, because we use forward differences in time. Yeah, we use forward differences in time because we want to have the information about the next time step from the previous one. Yeah. Therefore, a forward time difference is quite straightforward. By the way, there are we could also use a backward time difference. Then this would mean that we would have to solve an equation system, and actually this is good for stability. Yeah, so there are also possibilities to use backward finite differences in time, or even combine backward and forward finite differences. This gives rise to very interesting but more complicated schemes. You shouldn't hear this if this is your first day with partial differential equations. I didn't want to make it too complicated. But even with these simple things, you can already see that sometimes it's not easy to see why a problem shows up, why there should be a problem, and seemingly harmless things like using a forward or backward derivative may change a lot. Yeah, so not every scheme that you come up with, not every possibility to approximate a difference, a derivative by finite differences, not every choice is equivalent. Yeah, sometimes you have to do a lot of analysis to understand it. And this makes also the numerical part of partial differential equations a pretty hard subject. And if you see this for the first time, yeah, don't get desperate, because there are only so many important kinds of operators that can show up, and people over the years, people have learned how to cope with them and found recipes how to do it. But a lot of brain power had to be invested. Yeah? So don't worry if you don't see immediately after 5 minutes looking at a differential equation that the problem might be tougher than you expected. It took hundreds of years in some cases to understand what's going on. Yes. Yeah. Okay. Abdel asked a question about finite differences versus finite element methods. Yeah. Yeah. Actually, this is true. There are also finite elements methods, and vice versa. So there are different methods to discretize the equation, and I think finite differences are the easiest methods. In some cases, finite element methods and finite differences lead to exactly the same results, but only different formulations. Just to give you a hint, what is finite elements? What you do there is the discretization is you try to represent the solution. You compose the solution from, let's say, simple head functions. Yeah? So you have simple head functions. And so this is a head function, and this is a head function, and you try to compose the solution by overlaying a finite number of head functions, for instance. Yeah. And these methods have definitely their advantages. For instance, if you have irregular geometries, so they have many advantages over finite difference element methods, finite difference methods. Yeah? For instance, let's assume you have a complicated geometry, and you want to solve a solution, want to solve a differential equation on this here, compared to a grid. Yeah, on a grid, usually it's fine to have to introduce regular grids. Take this square or rectangle and subdivide it into smaller squares, and use finite differences to get the partial derivatives with respect to this variable or to this variable, and so on. Now, that would be finite differences, but here this is not a good choice. Yeah, so you would have to use a very fine grid to get this geometry described. And what you can do in finite difference, you can, for instance, use triangles to approximate this region. Yeah? So you can probably see it's easy, nice to subdivide this into triangles of different sizes and shapes, and this can be done with finite elements. Compare this to a very fine grid. You see that the approximation error is getting bigger. Yeah, so one of the things you should consider, if you have a very simple geometry like a square, which we often have, but not always, then finite differences might be fine. If you have a complicated geometry, then usually finite element methods are better, as a rule of thumb. There are also other methods, and it's a little bit related to what I will talk in the afternoon. I will not specify how this is working, but there are also so-called finite volume methods, and then you can use other geometries, so other methods like Fourier transforms, so-called spectral methods, to solve differential equations. So finite elements are only, finite differences are certainly only a part of the story. Yeah. Yes, and yeah, of course, Abdel is right. Yeah, is it not possible to use very small square grid to discretize a complicated geometry? Yeah, sure. It's possible to use very fine squares. Sorry, it's possible to use very fine squares. To describe this geometry here with very fine squares. But let's approximate it here this way. No? But the problem is very fine squares for each of these very fine squares. You have to compute the function on all these values, huh? On all these grid points. So you have a very large number of grid points. That's the main problem. While if you try to approximate this with triangles, you see that this might you will get away with a far smaller number of grid points, possibly. Okay, that's so you can save quite a lot of computational effort for complicated geometries. There are also things like adaptive grids that, well, let's say you have something like that you use a finer grid here and a coarser grid here. Possible, but this adds a lot of complication because remember, for finite difference, you have a constant delta x, you have a delta x here. And now if you combine information from one data point, which is so this, for instance, would have only a left neighbor but not a right neighbor. But maybe you need information from here. This is getting terribly complicated. And while for finite element methods, it's usually no problem when the size of the elements are rapidly varying. Yeah, so there's a question by Adeshina. Hope I didn't mispronounce your name completely. Is this the principle machine learning classifiers use? Not sure whether I understand the question. Tomorrow there will be a course on machine learning. I'm sorry, I didn't understand this one, the quant unity. Yeah. Actually, I don't see a direct relation to machine learning here. At least no uncomplicated relation to machine learning. There have been several attempts to combine solution of partial differential equations and machine learning. Yeah, for instance, you can use machine learning to solve partial differential equations, in order kind of learn the solution of a partial differential equation. That's also an active field of research. Yeah, rather than coming up with a numerical finite difference scheme or finite element scheme, you learn the solution of the partial differential equation. Maybe this is a little bit oversimplified. This is an active field of research. So definitely there are connections between partial differential equations and machine learning. But here for the finite difference schemes, I don't see a direct connection. Okay, yeah, but in biochemistry there are things like convection diffusion or reaction diffusion equations. Yeah, you have a substance which is diffuse. Sorry, yes. Let's assume you have a substance that is diffusing into sorry, again wrong. Let's assume you have a reservoir of a substance diffusing into the medium, and you have another substance here. Let's make this from different color, diffusing into the medium, and maybe these things can react with each other. Yeah, so this can be described by reaction diffusion equations, or systems of reaction diffusion equations. So partial differential equations certainly have a role also in biochemistry. Okay, then the question is the derivation of the continuity equation right? I assume, do you see a mistake there? Maybe. So if you found something that is wrong, please let me know. Otherwise, I think it's mostly okay. I think you can make a good exact derivation from it. Yeah? So what I did neglect is the error terms that we had here. Yeah. So this is a plus O of delta X. This is plus O of delta X. But I think otherwise it should be correct. But if you see an error, maybe you should let me know. Can also send me an email. By the way, I added my email address in the slides. So if you would like to reach me, use this email address. And if I see something before after the lunch break and before the end of the lunch break, I will try to correct it. Okay. Any further questions so far? I think we have 20 minutes left, if I'm not completely mistaken. Okay. So, yeah, if there are no questions from your side, we have several options. One option might be that we could solve, for instance, another differential equations using the method of characteristics, using Python, for instance. I try to solve a problem. Or I could, or we could discuss. I've inserted several exercises. And for instance, here by the method of characteristics, one exercise could be that we solve this equation, where we do, this is a case where we have a non-constant velocity, but the velocity depends on x. And this can actually be solved by the method of characteristics as well. So if there is no other question. So maybe then I decide that we do the solve this first exercise. Yeah, we try to solve this equation. Yeah? With the methods of characteristics, manually or using SymPy. And because this is a coding school, I would say the preferable way today should be SymPy. And what we do is we copy this one and just adapt this. So now, and what do we have to do? First, we don't need an A. This is without an A. And we only need the symbols x and t. U will again be a function of t and x. Ut is the...
sorry, Prof, to interrupt.
Yeah.
There is a question on Slack.
Yeah. Okay, so the question is, why did you consider using the tau function? So tau was a variable. Let me get back to the method of characteristics. Tau is a variable that says where we are on our characteristic. Yeah? So tau equals 0 means we are here in the characteristic. Yeah? So let's say this is t equals 1, t equals 2, t equals 3, and so on. Tau equals 2 means we are here on the characteristic. Yeah? And what we have to do is to find when tau equals t, what is where are we on the characteristic? Yeah, so tau is a parameter, yeah, running from here from 0 to t. Yeah. Here we are at 0, and now we are approaching t. Here we are at tau equals t. So this is a time, but a time which is a variable between 0 and t. Yeah. Why 0? Between 0 and 2? Because at 0, tau equals 0, we are at the characteristic intersects our boundary, where we have the boundary condition, u0, yeah, or what we called f. I should have called it f. So it's a parameter. Think you are sitting in a car at your point tx, and then you are driving with the car, or let's say you are sitting in the car on the boundary, and then you are driving along the characteristics until you reach time t, and then you stop and you see what is my x coordinate, my x position, and yeah, as soon as your x position reaches x, then you say, okay, I'll stop and I will copy the value of the initial condition where I started. I will copy it to this position tx. And this was, so the x coordinate, that was what I called psi. Maybe, yeah, so tau is a parameter which says us where am I on the characteristic? How much time have I spent on the characteristic in a way? And x, psi of x, this is where am I in space. Tau is where am I in time in the characteristic, and psi says where am I in space on the characteristic. And you can call it with every with a different name, of course. Yeah? So this is just a parameter. Actually, in many textbooks, it will also be called T, but this I find confusing, yeah, because T is the point where I want to know the solution. And X is the point where I want to know the solution. Yeah? So I hope this was clear. It takes a little bit of time to wrap your head around this concept. Okay. Yeah. And maybe I can provide you the solution for this with the manual solution. Oh, okay. Now let's change the problem. I copied the code, got rid of this variable a, and we replace a with x. Yeah. And now think of it. X is now basically. I thought I already told you what if you have a term factor times derivative with respect to x, you can usually interpret this in time-dependent equations as a term which describes transport by a velocity. So this would correspond to a velocity that is dependent on x, which means the farther you are away from the origin, the bigger x is, the bigger the flow will be. Yeah? And maybe this helps us to interpret the equation later. And we can come up with a solution. Let's see what Python tells us. Yeah, and this is what Python tells us. T of x is f. F is any function, an arbitrary function, times e to the minus t. And I can tell you, I've done this a lot of times with my students. If you apply the method of characteristics, I encourage you to try that. You get the same solution. Yeah. Now let's try to make sense of it. So Python tells us that uxt equals f to the x to the minus et. Yeah? And what Python doesn't say explicitly, if you look at the help function, we'll see that f is an arbitrary function. Arbitrary function. And I can tell you it's basically the initial condition. Or specified by the initial condition. Yeah. So our problem was we wanted to have, let me take the same formulation. U t, ut plus x ux equals 0. And the initial condition was f, u at 0x. So this is t equals 0. That is a specified function f, and actually it will turn out this is our function capital F, yeah, from that Python Python told us. Huh? So we test this, or the initial condition says for t equal 0, t equals 0, we must have u of sorry, should be the other way around. So I'm always mix up this. U0x, that should be a function f of x. And Python says U0x is f x to the e to the minus 0, t equals 0. Yeah? And this is f of x. And now we want that this is f of x. And this means we can just say f is our capital F. Huh? So whatever it was, say we have decided f should be the sign, then the solution would be, e.g. if U0x is sine of x, then u of xt would be sine of x to the minus et. That would be the solution of our problem. So the initial condition we have fulfilled, and let's check if the PDE is fulfilled. So we have to look what is ut plus xux. Now this is so del by del t of f of x to the minus t plus x del x f x to the e times e to exponential of minus t. Let's see what this gives. So this is the derivative. F is a function of one argument, but so we have now found a combination of the x and t coordinate such that the variable the function can be expressed as a function of this combination, x times e to the minus t. Yes, so this is the outer derivative, and we have to multiply it with the inner derivative, and that is x times minus e to the minus t. And yeah, sorry, yeah, this is correct. Huh? So plus x times, what is the derivative here? We have, again, it's a function of one variable, so same, x to the minus t. And then we have to take the inner derivative of this term here. So the derivative with respect to x, and this is just a factor e to the minus t. Okay, but this looks nice, yeah. So that means we have we can factor out this f x to the minus et times minus x e to the minus t from this plus x e to the minus t from here, and we see that these cancel out and we have 0. So we found our we have solved our differential equation together with SymPy. We were a good team. Excellent question. Good, very good. So Michael asks, can you explain why I got uxt equals f of t minus log x? Very good question. And actually, this can happen. Let me see if I. It's actually the secret is this is the same solution, or a similar formulation. Let me see what happens if I make this a function of x and t rather than. Okay. You see, by just replacing x by just interchange, making this a function of x and t rather than t and x, I got the same result as Michael. Yeah. So if I start with t and then with x, I get this result, and if I write x and t, I get this result. That's the same as Michael got. Yeah, interesting. Thing is, so sometimes this can happen. This can happen. It should not. Of course, the solution should not be dependent on the order of the parameters. Yeah? Yeah, because this is this defines the same problem actually. Yeah. So I guess Michael had reversed this. Thing is, both solutions are correct. Yeah. So if Michael checks his solution, it will also be correct. And the thing is, you can write this solution. You can transform these solutions. Yeah. What happens? So the reason is, let's take the logarithm of sorry. Let me copy what Michael had. So Michael had this solution, f t minus logarithm of x, and I had this solution, f x to the minus t. Yeah. So how do we come from here to here? So this looks strange, doesn't it? But actually, it's the same solution, because let's take the logarithm of my argument here. The logarithm of x to the minus et. We know the logarithm laws. The logarithm of the product is the sum of the logarithms. So we can write this as log x plus log. And keep in mind that log in Python means the natural logarithm, ln. Yeah. Log e to the minus t. So this is log x. And we know that the logarithm is the inverse of the exponential function and vice versa. Yeah? So logarithm and exponential functions are inverses of each other. So log e is just log followed by e, or e followed by log is just the identity. So logarithm of the exponential of t is just minus t. Yeah, yeah, and this is minus t minus log x. This is the secret. This is why yeah? So let's say this is f Uwe, this is f Michael. Yeah, and we see that so basically f Michael is f of logarithm x so minus logarithm x to the minus et. Yeah? So I think this is no the other it's the other way around. So I hope this makes sense. No? So basically, it's a change of variables. But I agree that is may look very confusing when you encounter this the first time. Yeah. So basically, both solutions are correct, and I encourage you to check whether this solution of Michael is also correct. No? You can check it by just doing the same calculation that we did here to check if this PDE is fulfilled. Yeah? So if you use Michael's function here, it would also work. Okay, so I think we are now moving into the break. I don't want to deprive you of a break again. And we will can proceed with the discussion later in the afternoon session. So have a nice break and see you again at, I think, 2.
Okay, thank you, Prof. Thank you, everyone. So we'll resume at 18:30 for our daily STEM talk. So I'll see you guys in an hour. Thank you, Prof. See you for the afternoon session.
So, okay.